Hello everyone, I am Pushpita Chanda. I am a PhD student in IIT Delhi under week2 program. My field is physics. I am a TA for Mathematical Methods in Physics 1 and this is second week. Am I audible?
Yes,
Okay, thank you. Now I will be sharing my screen and I will discuss the assignments for the week 2. Okay. Last week someone asked me to introduce row reduction in a elaborate way. So there we need to know there are two forms. One is row echelon form. Okay, sorry. Is row echelon form. Okay, sorry. One is reduced and another is reduced row. Okay, sorry for the inconvenience. One is row echelon form, another is reduced oh, reduced row echelon form. So what is the difference between row echelon form and reduced row echelon form is here. In row echelon form, the form will be the following. Here there will be a non-zero data. This is a non-zero, this is non-zero, but this will be a 0. Then it will be non-zero, then it will also be a non-zero. This will be non-zero. Again it will be a 0, it will be a 0, then non-zero term, and so on going on. For every for first row, first element will be non-zero. For second row, the second element will be the non-zero. For third row, third element will be the non-zero. For fourth row, fourth element will be the non-zero, and so on. It will be a form of stair. Echelon means stair. So this is called row echelon form. But for reduced row echelon form, these terms are called also the pivot terms, that non-zero terms. For reduced row echelon form, there are too many more constraints. This pivot terms has to be 1. and for first column, first row has to be only non-zero, and again another entries has to be 0. Similarly, for second row or for second column, only second row has to be non-zero, and that has to be 1, and all other entries has to be 0. For third column, only third row will be non-zero and it has to be 1, and all other entries will be the 0. So it will be the form of like this, 1 and so on. So this is row echelon form, and this is reduce row echelon form. It has to be a echelon form, but this pivot terms has to be the 1, and for first column only first row element will be non-zero. For second column only second row element will have to be non-zero, and for third column only third row element have to be non-zero. So let me discuss a example. Are the slides are visible?
Yes, ma'am.
Yes, okay. So here is an example. 2 2 minus 2 4 2 minus 2 do 2 1 10 7, then minus 4 4 minus 8 4, then 4 minus 1 14 6. So we need to reduce it to row echelon form, not reduced row echelon form, because from row echelon form we can do determine the rank of matrix and other forms. So this is 2. It needs to be a non-zero, but that has to be 0. Then this has to be 0 also, and this has to be 0 also. So if for any like row echelon, to make any matrix row echelon, we need to follow some step. First step is to make these entries 0 using row 1. So the first state of command are like this: R2 should be R2 minus R1, because then only 2 minus 2 will be the 0. R3 first entry is minus 4, so minus 4 plus 4 will be 0. So R3 need to be R3 plus 2 into R1. Similarly, R4 needs to be R4 minus 2 into R1. Following this state of commands, we will get a matrix 2 minus 2 4 minus 2. It will be 0. 1 minus 2 will be 3. It will be 6, then 9, it will 0, then 0, then 0, then 0, then 0, 3, 6, 10. Okay. Now we know some basic operation of matrix doesn't change the value of the matrix. One set of operation is this: addition and multiple of addition of 2 rows or multiple of any 2 rows, and also the row swaps. We have administrated that this row has already become zeros, so we can exchange these two rows. It doesn't affect the value of the matrix. So the next next matrix will be 2 minus 2 4 minus 2 0 0 3 6 9 0 3 6 10 0 0 0 0. Last row has become zeros. We don't have problem with that, but now we need to make this 3 0. So it is simple. R3 will be R3 minus R2. Here we need to write the command that R3 and R4 has been interchanged. So it will become 2 minus 2 4 minus 2 0 3 6 9 0 0 0 1 and 0 0 0 0. So this is row echelon form of the matrix, and from here we can say the rank of a matrix is is 3, not 4. So this is an example of row reduction. So now we should move on to the question of assignment 2. Assignment 2. So the question is, for each of the following system of equation, write down the augmented matrix and now row reduce it. From the row reduction form, state whether the system is consistent, and if consistent, find whether the solution is unique or not. So first, in the question we are asked that first we have to row reduce the augmented matrix, then state if it is consistent or inconsistent. If that condition is not given, then you can say otherwise how a matrix is consistent or not. If AX is equal to B, A is a matrix of coefficient, then if A is equal to 0 and B is equal to 0, then we have many solutions. If A is equal to 0, B not equal to 0, no solution. If A not equal to 0, B not equal to 0, then unique solution. Or B is equal to 0, then X is equal to 0. It is also an unique solution but trivial solution. But here we have been asked that we need to first row reduce it, write down the augmented matrix and row reduce it. So start the form of row reduction. First matrix will be 1 1 2 2 1 minus 1 and also 1 minus 1 3. First augmented matrix will be 9 0 13. Now we have to row reduce it. So R2 will be हाँ hello
आगे पेज पे एक बार चढ़ें मैम.
Okay, yeah. See, I have put the coefficients as a matrix 1 1 2 2 1 minus 1 1 minus 1 3 and this 9 0 13. I have written the augmented matrix. Is it okay? Hello?
Okay ma'am.
Okay. Okay, right. Then R2 will be R2 minus 2 into R1, R3 will be R3 minus R1 and that will be make A, if we put a name here A, so now A will become 1 1 2 9 0 minus 1 minus 5 minus 18 and this will be 0 minus 2 1 4. Now we need to make this minus 2 0 and for that command will be R1 will be R1 plus no, you can make it right that way. What? That R3 will be R3 minus 2 into R2 and that will be one 1 2 9 0 minus 1 minus 5 minus 18 0 and it will be 0 1 minus 2 into 11 and it is 4 4 minus that will be some value of like 36 plus 4 40. So here we can see that rank is 3 for the for this math part also and for augmented part also. So rank of A is equal to 3 is equal to, if we name that part M, so rank of M. When coefficient M is a coefficient matrix, A is augmented matrix. When rank of coefficient matrix and augmented matrix both are same and equal to the number of unknown, then it has a consistent the system is consistent and a unique solution. So the system A has a unique consistent solution. Now turn for system B. So system B will be 1, 2, 1 minus 4. 1 minus 4 minus 3, 6, 5 minus 8, 1, 2. So first this R2 will be just R2 minus R1, and R3 will be R3 minus 5 into R1. We will get the next matrix. It is matrix A, and only this portion is matrix M, and that will become 1, 0, 0, 2 minus 6 minus 18, 1 minus 4, 4, then 4, 10, minus 3, 2, like this. And then we will get 1, 2, 1 minus 4, 0 minus 6 minus 4, 10, 0, 0. R2, okay, this is R3. R3, 4 minus minus 12 plus 12, 16, and this is twin minus 8. So the rank of A is here also. 3 is equal to rank of M, so it is a unique solution. So question number B, it also has a unique solution. Now question option number C. The system C is one, 2, 3, 3, and 3, 2, minus 1, 5, 1 minus 2 minus 7 minus 1. First set of command is R2 is R2 minus 3 into R1, R3 is R3 minus R1, and we will get the form one, 2, 3, 3, 0, R2 minus minus 4, 2 minus 1, 3 minus 10, 3 minus 4, 0, minus 2 minus 2 is 0. Minus 2 plus 2 is not 0. Okay. It's plus 4. 10. It's plus 4. So the next can we say that R3 can be R3 3 plus R2, then it will be 1 2 3 3 0 minus 4 minus 10 minus 4 0 0 0 0. So the rank of A is equal to 2, and also the rank of this is A and only this is M. So rank of M is also 2, but it is less than the variables. Here 3 variables are there, x, y, z. So 2 is less than 3, that no unique solution. They are consistent solution, but no unique solution. Okay, so now we see the first option is A is inconsistent, so it is not true. Second option is A and B are consistent with a unique solution, but C is inconsistent. C is not inconsistent. Inconsistent solution are those for rank of A is less than rank of M is less than rank of A. A is consistent with a unique solution, B is inconsistent, that is also not true. A and B are inconsistent, that is also not true. So none of the above is the answer. Okay. Now find the rank of the following matrices. This is straightforward. 1 is equal to 1 1 2 2 4 sorry 2 4 6 and 3 2 5. First set of command is R2 minus 2 into R1. R3 is R3 minus 3 into R1. We will get 1 0 0 1 2 2 1 2 minus 1, and then 2 2 minus 1. Then we need to make this 0. For that we kind of write the row operation. R3 will be the R3 2 R3 will be the 2 into R3 plus R2. And we will get 1 1 2 0 2 2 0 0 and 0. So rank of A is 2. So here we get rank of A is 2, rank of A is 2, then our answer is from these two things. And for the trick, so when this is a MCQ question in exam, we can see either way it is a 4-mark question. You can derive the rank of 4 of the matrices, but you don't need to do that for MCQ part, right? Because in for 2 of the option, rank of B is 3, rank of B is 3. There is no contradictory statement. So, and we have already decided that from 4 of the options only 2 are the right, 1 and B. So we don't need to evaluate rank of B. We can evaluate rank of C or rank of D. After any of this rank, when we evaluate, we can determine which is the right answer. So C is 1 1 4 3, and here 3 1 10 7 4 2 14 10, and this is what 2 0 6 4. So first set of command can be R2 is equal to R2 minus 3 into R1, R4 is equal to R4 minus 3, not 3, 4 into R1, this is R3, and R4 is equal to R4 minus 2 into R1, and this will become 1 1 4 3 0 0 0 minus 2 minus 2 minus 2, this will be minus 2 minus 2 minus 2, this also be minus 2 minus 2 minus 2. How can this be minus 2? R2 minus 3 into R1. Okay, yes, R. I think they cannot. So this matrix will become this, and now if we can R3 is R3 plus R2 and R4, they are basically same. This 3 row.
Minus. That's minus, I think.
Yeah, all are minus 2. R3, yes, R3, yes. That will be only minus, and R4 will be R4 minus R2, because these 3 are same row, so it will reduce to 1 1 4 3 0 minus 2 minus 2 minus 2 0 0 0 0 0 0 0 0. So rank of C is 2. So in that option rank of C is 2, so we can now say that number 1 is right. You can also try to find rank of B and rank of D, that will come 3 3. Rank of C is when a 4 by 4 rank of a 4 by 4 matrix is 2. You can see that after 2 step you can see that it is rank 2. Now the third question: which of the following determinants is 0? For first, we can 0 2 3. If we consider this column, we don't need to do any row reduction form or something. We can evaluate this thing without any row reduction form. Sign for the expansion of determinant, this plus at a minus, this plus, this minus, this plus, this is minus, this is plus, this is minus, this is plus. So it will be 1, and cofactor of this 5 minus 1 2 3 minus 4 into cofactor 2 3 2 3. So this will become 0 and it is 17. So the determinant of this is not 0. Okay, now we will see the determinant of other. Determinant of 4. This is also you don't need to row reduction and all that. If you want to do that, it's fine, but for 3 by 3 expansion, you know, do not need that. 1 is 1 1 1 1, minus minus 1, it will be like cofactor minus 1 1 1 1, plus 1, it will be minus 1 1 1 1, so it is 0. Okay, this is plus 1 minus 1 minus 1, it is minus 1 minus 1, so minus 1 minus 2, and this will be, okay, sorry, this will be minus 4. So delta 1 4 is non-zero. Okay, here is question is delta 1 alone, delta 2 alone, these two are like eliminated, and now we need to check delta 2 and delta 3. If either of these non-zero, we can say that none of them, because here is no option like delta 2 is 0 or delta 3 is 0, because if delta 2 or 3 either of them become non-zero, we can opt out this also. Then by the method of elimination, only none of them will remain. So delta delta 2, it will 1 3 1 minus 1, and this is 0 2 4 1 minus 1 1 2 0 0 3 1 3. See, here it is all in for determinant expansion, like it will be very beneficial for us if one column becomes 0 or most of the elements of one column become 0. So we will choose this column. 2 are already 0, and we can make this also 0 by what? R3 is equal to R3 plus R1. It will become 1 3 1 minus 1 0 2 4 1 0 4 3 minus 1 and 0 3 1 3. So the determinant will be only 1 into 2 4 1 4 3 minus 1 3 1 3. Now you can expand that. 2 into 3 minus 1 1 3 minus 4, it will be 4 minus 1 3 3 plus 1 4 3 3 1, and it will add up to like minus 45. So it is also non-zero. We can see for matrix C also delta 3. For the sake of completency, that is what? Minus 103. Minus 1 103 3011 2 minus 122 and 2301. So there will be R2 is equal to R2 plus 3R1, R2, R3 is equal to R3 plus 2R1, R4 is equal to R4 plus 2R1. So that will become minus 1, 1, 0, 3, 0, 3, 1, 10, 0, 1, 2, 8, 0, 5, 0, 7. So now we can expand minus 1, and this is 3, 1, 10, 1, 2, 8, 5, 0, 7. Here you can expand about this row, that will be minus 1 and then 5. This is plus, minus, plus, minus, plus, minus, plus, minus, plus. So 5 into 1, 10, 2, 8, plus 7, 2, 3, 1, 1, 2, minus 1, 8 minus 20 plus 7 into 6 minus 2, 4, and that will become minus 12 plus, it will be 6 minus 4, 28. So minus 6 plus 8 minus 2, 12. Okay, this is not 2. This is 1. This is 1. So this will be 535. This will be 35. So 35 minus is equal to 25. Okay, then the answer will be none of them. For which of the following, question 4. For which of the following values lambda does the system of equation have infinitely many solutions? So I have already said, when we can write an equation like ax is equal to b, system will have many solutions when a is equal to 0 and b is also 0. So here we can see that b is 0. B is 0, 0, 0, x, y, z. A is lambda minus 1, 2, 1, 2, lambda minus 1, minus 2, 1, minus 2, lambda minus 1. This has to be 0. It is as simple as that. So get the value of the determinant. It will be lambda minus 1 whole square minus 4 minus 2 will be 2 into lambda minus 1 plus 2 plus 1 will be minus 4 minus lambda plus 1 is equal to 0. When you simplify all those things, it will be lambda into lambda square minus 3 lambda minus 6 is equal to 0. From this we can say lambda is equal to 0 and lambda square minus 3 lambda minus 6 is equal to 0. Lambda square minus 3 lambda minus 6 is 0. According to the rule, lambda is equal to b square 3 square minus 4 into a is 1 into c minus 6 by 2 into a. So it will be 3 plus minus 24 plus 9, 33 by 2. So one answer is 3 plus 33 by 2 and another is 3 minus root 33 by 2 and another is 0. So for three values of lambda, for these three values of lambda, the system will have infinitely many solutions. So right solution is 0, this and this. Now problem number 5. Problem number 5. NC, we need to determine NC, NR and RM. NR is number of independent row vectors. 2 minus 2 minus 3 5 3 4 minus 1 1 1 3 minus 2 3 4. So row vectors are, this is one row vector, this is a one row vector and this is a row vector. We need to see that they are independent or not. So just reduce it to row reduced form and see if the last row is non-zero and from there also we can determine the RM, rank of a matrix. So R2 will be the R2 minus 2 into R1, R3 will be the 2 into R3 minus 3 into R1. So that will become 2 minus 3 5 3 0 5 minus 9 minus 5 0 5 minus 9 minus 1. Then it is simple that R3 needs to be R3 minus R2. So that will be 2 minus 3 5 3 0 5 minus 9 minus 5 0 0 0 4. So we can say that number of independent row vectors, each row vectors are independent. So this is 3 and rank of matrix was also 3. Now we have to calculate the independent column vectors. So for column vectors, this is our matrix 2 4. Okay, sorry. Two minus 3 5 3 4 minus 1.
ম্যাম বলছি
হ্যালো, হ্যাঁ,
নাম্বার অফ ইন্ডিপেন্ডেন্ট কলাম
নাম্বার অফ,
বের করতে হলে কি আমাকে, হ্যাঁ ম্যাম শোনা যাচ্ছে?
হ্যাঁ,
ম্যাম বলছি নাম্বার অফ ইন্ডিপেন্ডেন্ট কলাম বের করানোর জন্য কি আমরা কলাম অপারেশন করব নাকি রো অপারেশন করে
Okay.
বের করানো যাবে?
Okay. This is the trick here in the assignment. They have used that, like, oof. And what is this? 3 minus 2, 3, 4. The proper rule is do the like column operation, but we do row reduction every now and then to know the rank and to know the if the system of linear system is consistent or non-consistent. So if we do not want to burden our head with another type of operation which is row transpose of this matrix and do row reduction and then again transpose it, so you will get the column reduced matrix. Okay.
Okay ma'am.
When you transpose the matrix and then do the row reduction in the similar way, in column reduction, in row reduction you make this 0. In row reduction you need to make this and this 0. You can do it by let me show you. It can be done by the column operation also. Then C2 will be 2 into C2 plus 3 into C1. C3 will be 2 into C3 minus 5 into C1. C4 will be 2 into C4 minus 3 into C1. So the columns will be 2 0 0 0, 4 10 minus 18 minus 10. Then it will be 3 5 minus 9 minus 1. Okay. Then you need to make then you need to make this 0, then these two things 0. Yeah, then you need to make this 2 0. Or first you can take common from this 2. Okay. So 0 0 0, you need to make 4 10 minus this has to be 0. So how can just plus this thing, so C4 will be C4 plus C2. So this is 3, this is 5, and plus 5 minus 1 4. And to make this 18 0, it is like C3 will be 10 into C3 plus 18 into C2, that will be 0. 10 into C3 will be 19 plus 18 into 5, that is 98, it will be 0. Okay, so we can now interchange like column interchange. So what you see, 2 4 3 0 10 5 and 0 0 4, one column has become 0. Then the number of independent column vectors is 3. Number of independent column vectors is 3. Understand? Because one column has become 0, we have only done column operation. So by only column operation we can see that number of independent column vectors is also, what was that, NC. NC is 3. So what is different here? Here in row reduction we make this thing 0 and this thing 0. Here we have to make this thing and this thing 0, then that and that 0, then that is 0. Here after 2 operation we can see that one column has become 0. So if you think that column operation are after doing row operation, column operation are a little bit tricky, then transpose it the matrix, then do the row operation, then again transpose it. It is the same. Okay. One minute. My laptop is not responding, so please have patience for 1 minute. Yeah, then we can say the option number B is right. Yeah, option number B is right. Now question number C. Did you understand what I have said for question number 5?
Yes.
Yes. See, for this to obtain rank of a matrix or number of independent row vectors and independent column vectors, you just need to reach the row echelon form. Okay, not reduced row echelon form. I have already said one is row echelon form and another is reduced row echelon form. In reduced row echelon form, it is or more steps again. So just make those things 0. Make those things 0 as long as you are making these things 0, this 0, you are good to go. So this number 6. u1 and u2 be the two subspaces of a vector space. Subspace of a vector space is a subset of vector space which form a vector space which is also a vector space, but subset of V that follow all the rule of vector space. That is it. The set of all vectors that belong to both u1 and 2 is called the intersection of u1 and u2. So u1 u2 means they belongs to un and also belongs to u2. Which of the following statement is true? See, u1 intersection may or may not be a subspace of V. So we need to prove whether u1 and u2 is a vector space under the same condition, closure property. If they follow closure property, closure under vector addition and multiplication, scalar multiplication, vector addition and scalar multiplication, identity and inverse, right? If we think that a vector is x and y, they belong to u1 intersection u2, then alpha x plus beta y, this is closure property, we already know that. Okay, will it be belong to like u1 and u2? If x belong to u1, y belong to u2, then alpha x plus beta y will belong to u1. Similarly u2, so we can write this belongs to u1 intersection u2. Good, no problem. Identity. Zero vector is the identity of zero. If we add x alpha x plus beta y, if we add 0 with this, we only get alpha x plus beta y. 0 belongs to u1 intersection u2, and the inverse of this also belongs to alpha. When alpha x plus beta y belongs to this, alpha x minus beta y also belongs to u1 and also u2. So we can say that it is a subspace of V. Then question number 7. Suppose A and B are linear operators on some vector space V. Which of the following statements about the operators A, B and A plus B is true? Linearity is like if like say A is an operator operating on a state, it will give Y. Then B operator will also give something x1, so it will give not y, something else, or you can assume that it will give y. It is no other thing. Okay, so we need to define if this thing will give a plus b and ab is linear or not, and this x and y both belongs to a vector space V. So For linearity we can check two of the property like this. If a plus b operating like a plus b operating of a operator x and it gives us back ax plus bx, then we can say that this x and y definitely not equal to this y. Okay, like it is an example. And if b is operating x and on x, it will give y1 x1 y1. Keep it simple, like a is a operator which is operating on alpha x plus a plus b beta y. So it will become a alpha x plus b alpha x plus a beta y plus b beta y. To keep all the, it will become alpha a x. This will become alpha beta x. No, alpha bx. This beta a y plus beta here b y. So alpha plus we can take common and this will be alpha so it will be a alpha x plus beta y. You can take common from this, plus b into alpha x plus beta y. So a plus b alpha x plus b alpha x plus beta y give you this a alpha x plus beta y plus b alpha x by beta y. If you if you think it is a little bit complicated, then remove this beta y portion. A plus b operating on alpha x will give you the same, like remove this portion. Okay, so it will not be that cumbersome. So a plus b alpha x a plus b alpha x a alpha b x, and it is like here it is. So up to this is fine. And for AB, if AB is linear or not, we can write, see, AB alpha x for that only you can do alpha x plus beta y. Here to prove that a b alpha x plus a b beta y, then it is alpha a b x plus beta a b y. So it is also distributive, and both a plus b and ab is linear. Any confusion in this thing? You can also check a plus b on alpha x plus beta y also, which I have done earlier. But if you think it is very much complicated, then when you prove a plus b, only alpha x is sufficient. Question number 8. Question number 8. Let us consider the set of n distinct vectors which are all part of some vector space. The vector 0 is the null vector which, if the following statement is true, this is necessarily a dependent set of vectors, this is necessarily an independent set of vectors. This may be a dependent or independent set depending on the specific vectors chosen. This would be a dependent set only if all vectors in are orthogonal. No, all orthogonal vectors are the vectors which are orthogonal to each other will be independent. Okay, the last option is not true at any cost. Okay, so let us check a0 a1 x1 plus a2 x2 and so on. It is an minus 1 xn minus 1 is equal to 0. If they are all independent set of vectors, then this coefficient has to be 0 to make 0. So it is a null vector, so it will become 0, right? So this thing is already 0. So what remain the a1 x1 plus a2 x2 an minus 1 xn minus 1 0, right? So here we can see that 0 can be represented by, when we omit, like for independent vectors, for these all vectors to be independent vectors, this condition has to be satisfied. But when a coefficient is there is a coefficient with a vector 0, it will become 0. Then this a1 to an minus 1 up to n minus, they are independent, but 0 can be written, it is a 0 vector, 0 can be written with the combination of these vectors x1 x2 x3 and so on. So you can see that this is necessarily not an independent set of vectors. This may be dependent on independent set depending on specific vectors chosen. It is not like that. So this is necessarily a dependent set of vectors because 0 is in this vector space and 0 can be written with all other vectors. Again, consider the following 4 set of vectors. Mark all the sets that form a basis for the usual space of 3-dimensional vectors. So A is written like that, E x 1e x plus 2ey 3ez, it can be written like this: 1 2 3 4 5 6 7 8 9. It is a very good matrix. So again, is it independent or not? The foremost technique is to see if the determinant is 0 or not. But we also know if one row becomes 0 for this matrix or determinant, the determinant becomes 0. If it is becomes 0, determinant is 0, then they are not independent vectors, they are dependent vectors, and dependent vectors is not a good basis. So let us check which will form the basis vector. One, two, three, 4, 5, 6, 7, 8, 9. So there you need to do some row operation. It is as simple as that. Like, it is not need to make the row operation like to form row echelon form. It is like it is a special if we want to see if one row is 0 or not. R2 minus R1, R3 to R3 minus R1. Here you can see that 4 minus 1 is 3, 7 minus 4 is, it is R3 minus R2 minus 4 also 3, the difference is 3, so 1 2 3, it will become 3 3 3 3 3 3. So then when you make R2 minus R3 minus R2 is R3, it will become 1 2 3 3 3 3 0 0 0. So one row is 0, so A will not form basis. Why we have done this? Because here we can see the difference is 3, here also 3, so it's like intuitive. Then the next vector, it is a next vector.
Ma'am, dependent or independent vector is not a good. Please repeat again.
Oh, okay. If they are independent vectors, then it is a good basis. Okay. Or you can say only independent vectors can form a basis. Not about good basis and bad basis. Like keep all the things black and gray, black and white. Nothing something gray. It is base. It will form basis if they are independent. It will not form basis if they are dependent. Okay. So you can check if these vectors are dependent or independent via directly calculating determinant. If you calculate the determinant 1 2 3 4 5 6 7 8 9, it will be a lengthy calculation. It's not difficult, I say lengthy calculation, but it will give a determinant 0. Okay, you don't need to all those things like intuitive row 2 minus R2 minus R1, R3 minus R2 and all that. Directly just determine the determinant. It is enough. So here 1 minus 1 1 1 1 minus 1 minus 1 1 1. Just take the determinant. 2 1 minus 1 1. So 1 1 minus 1 1 minus plus 1 1 minus is equal to 4. So they are independent vectors, they can form a basis. Okay. Then check 3 by 3 matrix. See the vector base, will they make 1 2 3 4 minus 5 6 7 8 9. When there is plus 5, it will not make basis. See if minus 5 will make. Okay. Here like to make determinant calculation easier, you can make this 4 and 7 0, which can be made by like 0 13 6 and like 0 6 12, or you can like R2 is equal to R2 minus 4 into R1, and R3 will be R3 minus 7 into R1, or you can directly take the determinant. So it will be 13 6 6 12. You don't need to do the calculation till the last point, you can already clearly see it, that is not 0, so it will can form basis. Okay. When you are attempting this kind of MCQ and you are sure about it, your intuition, from this you can see that it will not be 0. And the 4 will be 1 minus 1 minus 1 minus 1 1 minus 1 minus 1 minus 1 1. So if we do R2 is equal to R2 plus R1 and R3 is equal to R3 plus R1, it will become 1 minus 1 minus 1 0 0 0 minus 2, that will be 0, this will be minus 2, this is 0, so this will be 1 0 minus 2 0. So this is also not equal to 0, it will be minus 4, something like that. So they will form a basis. Mark all the set values for usual. So this will be B C D, and always remember that this matrix where 1 2 3 4 5 6 7 8 9, their determinant is 0, and that's why it will not make if they are written in this orientation or in this sequence, then only. If there is another sequence, then you have to check, you should check them. Okay, what? Choose question number 9. That was 8. Then question number 10. let 1 and 2 be a basis vector for a vector space where 1 and 2 are distinct vectors of the space. 1 and 2 make basis vector for a vector state and they are also distinct vectors of the space. Now A is 1 plus 2 and B alpha 1 plus, okay, it is not like that. A is a space which consists of 1 plus 2 and 1, alpha 1. It is consisting of beta 2, where A not which of the following statements are true? Both A and B are bases. Only A is a basis, to B is a basis, and neither A or B is basis. So basis means they have to be linearly independent, nothing else. So like anyhow, C1 1 plus 2 plus C2 alpha 1, they are 0, then that will be C1 plus alpha C2 1 plus plus C1 2 is equal to 0, right? It is the calculation. So 1 and 2 are the basis vector already. To add up those vector with a coefficient and make it 0, we need to C1 plus alpha C2 is equal to 0 and C2 also 0, C1 also 0, sorry. C1 0. So they have to like independently this coefficient of 1 and coefficient of 2 has to be 0. This means C2 need to be also 0. Then 1 plus 2 and alpha 1 is a independent linear vector and they can form a basis. Similarly, we have to check for B. B is what? There we need to give this kind of notation, otherwise it is not right. So C1 alpha 1 plus C2 beta 2, this has to be 0. When we say 1, some combination again, let us say 1 2 is 0, this is given. A1 is some constant, A2 is some arbitrary constant, then C1 alpha is also an arbitrary constant and C2 beta is arbitrary constant. The only one way to make this sense is C1 alpha is equal to 0 and C2 b is equal to 0. So alpha 1 and beta 2 are also linearly independent vectors. So they will form basis. Here both A and B are bases. From here it is also you can say alpha and beta are scalar. They are scaling 1 and 2. Like when 1 and 2 you can treat as them x and y. It is an example, like they are not x and y, but like treat them where 1 is x and y and 2 is y. They form basis, we know that they are Cartesian coordinates. So alpha can be anything, 2, alpha can be 2, 3, beta can be 4, 5. So if you scale, like instead of x you take 2x and y, 3y, 2x and 3y also form a basis when x and y is a basis. Okay, is that clear? Any other confusion you can say? Or I can make those calculations which I have skipped to make it fast. Like this rank of matrix, I only have calculated rank of A and rank of C. I can calculate rank of B and D also. Okay, clear. Then let me calculate rank of B and C here. All do know the answer. B is 2, 3. Okay, B, what is B? 2 minus 3, 5, 3, 4, minus 1, 1, 1, and 3 minus 2, 3, 4. So here R2 will be R2 minus 2 into R1. R3 will be 2 into R3 minus 3 into R1. Then it will become 2 minus 3, 5, 3, 0, 0. R2 minus 1 minus indefinite choice 5, that will be 9 minus 9, and this will be minus 5, and then 2 into R3 minus 4, that will be 5 minus 9 minus 1, and here we can see R3 is equal to, can be R3 minus R2, 2 minus 3, 5, 3, 0, 5 minus 9 minus 5, 0, 0, 0, this is 4. So rank of B is equal to 3. So from this line also you can see that if it will be, if this minus 1 would be minus 5, then the rank of B would be 2, but it is not minus 5, it is something else. Then whatever you can do, you cannot like make all the 4 entries in the last row 0, so it will be 3. Then rank of 1 0 1 0. So R2 will be R2 will be R3 minus 2 into R4 will be 4 minus 2 into R1. 0 1 0 0 0 2 3 3 and will be 0 4 6 6. You can see this row is the multiple of 2. So when you do actual form of row reduction, you need to make this 2 is 0. So do that. 1 0 1 0 0 minus 2 0 0. So R3 will be R3 plus R2, and R4 will be R4 plus 2 into R2. So this will be 0 0 3 3. This will be 0 0 6 6. Now you need to make this 6 vanish, and one zero 1 0 0 minus 2 0 0 0 0 3 3 0 0 6 6. This just R4 equal to 4 minus R3, 2 into R3. So that will become 1 0 1 0 minus 0 minus 2 0 0 0 0 3 3 0 0 0 0. So rank of D is 3. We have already from rank of A and rank of C, we we opted the option 1, which is rank of B is equal to 3 and rank of D is equal to 3, and now we have seen that that is also true. And where it is in this equation, this is delta 1.
Ma'am, I have a question.
Hello?
Ma'am, I have a question.
Yes, tell me.
Ma'am, please give some example of row linear matrix and linear matrix.
Give you an example of linearly independent matrix and dependent vector or matrix.
matrix.
Okay, linearly independent. Give you the example. I don't have on the top of my mind, but you can see that one we have. This is a dependent matrix. Okay, and also like
Row matrix.
row matrix. I don't
Yes, ma'am. ম্যাম এখানে একটা কোশ্চেন বলেছে যে রো ম্যাট্রিক্স এর মধ্যে লেখা আছে -1 -1 5 0, সেকেন্ড ম্যাট্রিক্স এর মধ্যে লেখা আছে 16 8 -3.
Okay.
Third matrix.
First matrix, which is row, 3 row matrices has been given. Okay, right?
Yes.
Yes. First matrix is 1A is equal to, tell me.
-1 5 0.
5 0. B is
16 -3.
8 minus 3. C is
-64.
minus 64.
56 and 9.
56 and the 9. If they are linearly independent or not.
Yes, ma'am.
So it is simple, like you need to make a matrix which is -1 5 0 16 8 minus 3 minus 64 56 9. Okay, and determine is determinant, so this determinant will be -1 5 0 16 8 minus 3 minus 3 64 56 9. This is -3, right?
-64.
-64. Okay, so choose this. If you don't want to do any row and column multiplication and all those things, it is very simple, like it will be a lengthy process, but just -1 8 minus 3 56 9 minus 5 16 minus 3 minus 64 9. So -1, number 72 plus 168 minus 5 144 minus plus minus it will be like this, -1 at 168 72 240 minus 5 144 192 48 minus 48 minus 240 plus 240 to 0. They are dependent vectors. What is the answer? Hello?
Yes, ma'am. Linearly dependent.
Yes, they are linearly dependent vectors. Like form of matrix, 3 by 3 matrices, and see if the determinant is 0 or not. And there is also a form, row deduction form. They are dependent means one of the row is the multiple of other, some kind of multiple of other, or some other combination. Okay, if you buy like, okay, here like minus 3, 9, 8, 56, 16, 64, or one row will be some kind of multiple or linear combination of two other row. If you by by a look, if you are certain that it is something, some kind of like combination, you can then and then say it is a linearly dependent vector or basis. Like in 1, 2, 3, 4, 5, 6, 7, 8, 9. What you can see, there is a difference of 3, right? R2 is R1 plus 3, R3 is R2 plus 3, or you can say R1 plus 6. So they are not three different bases, they are only one basis. Okay, they are not linearly independent, they are dependent. Similarly, 1, 1, 1, 1, 1, 1, 1, 1, 1, it is hidden there, like it is independent. So always the rule is dependency, whether it is linear independent or dependent. This will give determinant not equal to 0, and this will give determinant equal to 0. That's it. You don't have to like row reduction and other multiplication and blah blah blah. Simple follow, expand the determinant and put the value of determinant, like omit the value of determinant. When you need to use like 4 by 4 matrices like this, then for your simplicity make all these things 0, then only your determinant, like one question was there na, the determinant, see the determinant I have like for determinant 1 and determinant 4 I did not like do any operation. Like if you need more time to think the operation you want to do, it is not worth it, just calculate it as it is. But for 4 by 4 matrices, make this term 0, just reduce it. When you make this thing, it already reduced it to 3 by 3 matrices or 3 by 3 determinant. Then follow the procedure to expand the determinant. You don't have any problem then. But for when you have full 4 by 4 determinant and you do conventional determinant expansion, it will take you more time. Then follow the method that keep like in one row or one column, make all those things 0, and then follow the procedure like expand 3 by 3 determinant. Am I understandable?
Yes, ma'am.
And for other application, when you need to like obtain the rank of a matrix or something, that then you have no other choice, you need to like you need to go through that row reduction formula and all that. But for other purposes, if the matrix is if the row vectors are linearly independent or the column vectors are linearly independent, then see that you don't need to like think of those complicated command R2 is equal to 2 into R3 plus 5 into R1, so that the determinant looks very simple, became very simple. In your 11-12 level mathematics, matrix and determinant problems, you have also seen alpha plus beta plus alpha 1 plus beta 1, like this kind of thing. There you know that you have to do something like that. In those things also, when you need to the value, if you like follow the procedure and simply expand the determinant, it will, if you do the correct mathematics, it will give you this like same value. But if you do those kind of command or use those kind of command, it will simplify your calculation. But to think those kind of command, if it is taking more time, it is more consuming, then it's not worth it. Okay.
Ma'am, I have one more question.
Yes.
The rank R of the product of an M cross N matrix A of rank RA and an N cross P matrix of rank RB satisfy the given 4 options. One is RA plus RB minus N less than equals to R.
Okay, Payal, you can do one thing. You can send me that question via mail. I'm not understanding. I am giving you the mail address of mine. Okay.
Okay.
Or you can post it on the forum. I don't know it is like adjustable or it. Or can you share the question? Hello. Actually,
Yes,
I don't know. Can I share my personal information on this platform or not? Like that is my personal email ID. You can share or post that on the forum. If you want to share, I will unshare my screen and you can share that thing, and I will get back to you in the next class. Is it okay? Hello, Payal? Payal? Okay. And I'm not seeing any question here. Okay. The rank R of the product of M cross N matrix of a rank RA and N satisfy. Okay, I'll solve this question and get back to you in the next class. Any other question, Payal? হ্যালো,
হ্যাঁ ম্যাম এ পর্যন্ত ঠিক আছে।
Okay, then I'll give you the solution for this question in the next class. Okay, then let's finish this class. Have a nice night ahead, because it only remains the night this day. Okay, bye.